Hello and welcome back to Emulating RISC-V in a high-level language, where we have fun building an emulator for the RISC-V CPU in C Sharp. And it's been a little while since my last session, summer break and all that. Now we're back, energized, and we're going to take a look at how we can enhance the state of the project where we're in right now. So we should hop over to the code and take a peek at what we left with so far. So we have here our assembler file. We have an asm function, which takes a bunch of numeric parameters, and then depending on which operation you've chosen, we have a switch statement that vectors off. And this operation intrinsically knows the format for each one of the instructions. So if you ask for an add instruction to be assembled, then we use the R format of the instruction to generate the output. And so we trundle along, basically looping through all of our operations and doing a switch. Now, when I left off, I had implemented maybe a dozen or so instructions. The RISC-V specification introduces quite a few more, and I thought it would be a service to the viewers to not have to force you to watch me implement all of those method, uh, all of those new instructions online. So I did those offline, and I ended up adding unit tests for the assembler. Let's take a look at those. Where are they? Here. And we'll see that the assembler was changed to add quite a lot of new instructions. So here's a whole pile of new instructions that the assembler now understands. The emulator hasn't been updated to match all of those instructions because it takes a lot more time to write a proper emulation of instruction than it takes to generate the assembler. The assembler the assembler tests that you saw there, they were all generated from extracting the text out of the specification and then doing a search and replace. So this is all very mechanical. But if I run now all the unit tests, they should all pass. Indeed they do. So let's go ahead and add those so that we can start with a nice um, stable starting point. Okay, so so what I wanted to talk about today was the something that we've been skimming over and overlooking, but which is kind of important if you want to do any real amount of assembly language programming. So let's go back to our main program, the driver, the RFV fun main program. And as you can see here, this this is one of our programs that we've written. This is actually a simple version. It doesn't have any loop control. But one of the things that I notice is there's a lot of repetition going on here. And this repetition is tedious because it makes it harder to read the program. And also, it's very verbose. I mean, this ASM directory is duplicated over and over and over again. And I was considering, well, what if we just added a method called add_I, which would be a method on the assembler itself, and it would do the assembling of the add_I instruction directly. So I thought that would be nice. And then, um, well, why don't we do that? Why don't we just add methods for all of our assembly instructions? So whenever you see an add_I inside of the ASM, we would replace it with a direct function call to add_I like this. That would make a lot more sense because then we would have less typing. and this is good leading up to something further on. So let's start by refactoring the add I instruction and all the other instructions. So what we'll do is we'll go to our assembler, and what we'll do is we will do the following. Every single one of these cases consists of a case and a mnemonic, and then a colon, and then the assembler directive that we wish to execute. So my idea is that what we want to do, let's start with add I as our canonical example. So add I is here. So what we want to do is create a new method called public void add I, which takes the three operations. We no longer need this parameter because it's implicit in the function, but we'll grab all these, and then we also know that add I doesn't need these extra parameters. So we will just, oops, I lost my clipboard. This would do the trick right here. So if you call add I, then this would generate the I instruction type as before. So really what we want to do is just repeat what we just did for all of our instructions. And one way to do that is to take a usual array expression, as I am fond of doing. So why don't we do that? So right here, we'll put all these instructions. And now we write the array expression to clean or convert them into these little function calls. So let's create our array expression. We will trap anything that's start with case, mnemonics, and let's use regular expressions for this, of course. And then we want to capture the word that comes after the mnemonic and then the colon. Um, so now we've captured the add, then we want to capture the new line, any number of spaces, and then we have asm r. So this is the code that we actually want to execute. So everything following the spaces and then a semicolon, but then we want to ignore the break. Okay, so that is, now we've captured the mnemonic and the um, the actual assembler, the asmr, asmi, etc. So now what we'll do is we'll create the replacement, which is going to be a public method called, the first capture is the name of the instruction, and we're going to initially use dest source 1 and source 2. Then we can refine this later. And then in here, we will then take the second part, or the second capture, which is the actual assembling instruction. And then we create a new line and then ending curly brace and two more new lines. Let's see what that does. So that looks sane. We might want to give it a few more spaces. All right, let's see the next one. We will reformat this document once we're done. Okay, so I also have a syntax error here. We'll have to put an int there. All right, let's find the next one. That looks good. All right, this looks really good. So as I said, this is a refactoring doing, I'm doing this more for the comfort of the programmer. I mean, the functionality of the program is still the same. We can still call the asm method if we wanted to, but it's just a little less typing to call these instructions that way. Okay, I've got to slow down a little bit now. We're reaching the last instructions. Okay, there we are. So that was that. All right, now we have a few errors. Let's fix those. The first one is we left out the int here. Let's fix that. And then here's another add I. Now this is a duplicate of this. I'll just remove this first copy here. All right, and then there's a few more. That's a typo. Okay, so there we have it. Our assembler has now hopefully no more warnings. So let's give it a shot. Let's change all this so that wherever we have m.asm and an opening parenthesis, we'll just replace the and then a mnemonic. We replace that with the mnemonic. Let's try replacing this. Oh, we're failing to capture. Oh, we need to eat the comma that follows the mnemonic as well, and the space. All right, nice. Okay, cool. So now we have a little less clutter in our code. And this also brings to attention, we see this pattern where we want to create a small constant. We use the add I instruction to do this because this is how RISC-V rolls. But that's also very tedious. I mean, why do I have to specify R0 all this time? So in assembly languages, and that's not just limited to RISC-V, it's very common to provide what is known as pseudo instructions, which are instructions that syntactically look different from the underlying instructions that they assemble to. We're going to introduce now a RISC-V pseudo instruction called li, which means load immediate, and we will write a test for that. As usual, when we add new code, we have to make sure we have a test. So here, oh, and by the way, I'm going to leave these as ASM directories, but incrementally, I might decide to update these to not use the ASM function call. But we'll add a new method now, near to add I. Let's find add I right here, okay? And we'll change it so that it looks like this. So load immediate will only take two operands, the destination operand and the middle operand is ignored. So what this should do is yield the same result as if we had said load immediate, destination register is the same, but the first source register will always be 0. And the net result of this is that we always load an immediate value that is specified as the second parameter directly into register 1. The net effect is the same as the add I 0 and then -2. So we're adding a hidden 0 to this load immediate instruction. So let's go add li to our assembler. And this file is becoming very big now, but this would be the place. So public void li, we have a destination and an immediate value. And what we want to do then is asm I and use the same opcode as add I. So we'll take this and then adapt it. So we don't have a source 1, we'll just pass a 0 and then get rid of this trailing break and then use this variable for the immediate value. So this now Oops. This now should do the same thing as unload immediate, or sorry, as an add I. So with the understanding that the first source operand is always going to be 0. And thus we have a load immediate which will load small numbers into the destination register. And this makes, well, let's run the unit test first, make sure that everything is still hunky-dory. And then let's change our program so that it becomes even more clear what it's doing. And a lot of you who have been suffering along so far are maybe a little bit relieved now because these add I's certainly aren't that intuitive. I mean, we're not doing really an addition, we're doing a load. And so let's replace all those with load immediates. Let's see. Let's remove that. That's a load immediate. This is a load immediate. This is a load immediate. In fact, all of them. Every single one of these instructions is an immediate load. Nice. Oh, and we call has to stay the same. Yeah. Um, good. So if we run this program, we should still see hello world. Oops, and I started the wrong program there. My bad. Let's try it again. Let's see. Let's run our program. I need to change the tasks here. So right now it is running. Interesting. Rather than struggling with this live on stream, we'll just run it from here. And there's our hello world, still working as before. Interesting. Okay, so we've added li. Why don't we commit those changes as well? Might as well put them out. So let's add a little more helpful comment here. All right, there. Now let's tear away the the factorial code, or sorry, the hello world code. We don't need this anymore. What we want to do is instead go back to our example where we were computing the factorial of a function. And so to recall, what does that look like? Well, you start with a number n, which is some number that you wish to compute the factorial of, and then you have a while loop that says while n is not equal to or larger than 0, we will do factorial is equal to 1. That's the starting value of the factorial. And while the number n is larger than 0, we will do n equals n, or factorial, sorry. Factorial equals factorial times n, and then n is equal to n minus 1. And then we print the result, and the result will be in, yeah, there we go. In register, let's make that actually, let's think about this. We change the emulator execution. Okay, yeah, we'll put the result in register 10. Okay, so what we'll do then is have the result be, the factorial be in register 10. So we'll do the same process that we did before. We'll rename factorial to x10. Not sure what's going on here. Well, I guess we'll have to do it manually. And then n, I guess we'll call x11. All right, now we need to convert these to assembler instructions. So that should be easy. This is an li of register 11. And we give it the immediate value 10. And then similarly, register 10 gets the immediate value 1. And now the while loop, we have to check. But let's just change the way this is done. So we'll give a destination of register 0, and then the target is going to be some unknown destination. And this is the problem that I was referring to earlier. How tedious is this? I don't know how far away I'm going yet, so I'll just have to leave a marker of some kind that says this needs to go to the head of the loop. And then we create the body of the loop where we say, now this is a multiplication, so we'll say multiply 10, 10, 11. The next one is subtract immediate or add immediate. Here we do want to add immediate because we're incrementing the contents of the register by -1, thus making it smaller. And now we want to do the comparison. We want to say, um, is x11 bigger than 0? So we'll say uh, branch if. So we want to continue looping if we're greater than, which is the inverse of less than. So if 0 is less than, register 0 is less than register 11, then go to, and again we need somewhere. This would be the loop body. And then here at the end, we are done. So this is our factorial. We can get rid of this now. So the problem now is we have to determine what these displacements are. Remember, these are byte. So the difference in address between the current location and the address that we wish to go to, which is this address right here. This is the head. Now, wouldn't it be nice if you could just say, this is the head of the loop? So I would love to be able to say label and then say loop head. And then here, I would, instead of having to compute the destination, I would just want to be able to say loop body. And similarly here I'd like to say loop head. So unfortunately, we don't have these overloads of the jump and link uh, and BLT instructions, and we don't have the loop body either. So for now, we're going to have to compute these manually. So again, we bring out our little calculator and start computing. This is address 0, this instruction here. Now this instruction is address 4. This is address 8. Okay, remember 8. And then this is 12, and this is 16, and this is 20. So the difference between 8 and 20 is, let's make sure we didn't, yeah, exactly. 8 and 20 is 12, but I counted the label instruction, which is not a real label. Let's comment this out. So Again, this is at address 8, this is at address 12, this is at address 16, this is at address 20. So, no, I'm not doing a good job here. Address 8, address 12, address 16, this is at address 20. The difference is, hmm, skip 4. Oh, yeah, all right. Well, it is correct. I'm not sure why I'm double guessing myself. So we want to skip ahead 12 bytes. That's what that does. And then this guy wants to jump back. Well, -4, -8. So this one wants to go back -8. And let's fix jump and link and because we never use source2, so we might as well not have it passed in to the method. Okay, so this should compute factorial just like we did before. Let's verify that that is the case. Oh, we're failing. I missed the semicolon. All right, let's try that again. Oh, we have to print out the value. Also, hold on a second. We expect the result to be in value in register 10. So, all right, let's debug this. Something is not quite right here. Hmm. Right, I have this issue. It's running the tests as if it were the I'm not sure why the environment wants to execute the tests rather than my. Well, .NET Run does prove that the code is executing correctly. This is 10 factorial, just as expected. All right, so let's go back now and go back to uh, wishing for a way to write this loop using this label, loop head and loop body. Let's add a label here. So we don't have this method label. So why don't we just write it? So what this will do is as we assemble our instructions, when we encounter a label, we look at the current instruction pointer value and save it away someplace. And then we can then refer to that later. So let's implement this method. And what we want to do now is what we want to now is create what is known as a symbol. A symbol is a combination of an address and a name. And so let's create a little class for that. So a symbol is a name and an address I want we to create one of these things by calling its constructor. And then in the constructor, we will assign the properties. Okay, so as we assemble, we start collecting the symbols that we encounter from these label statements in something called that we're going to call a symbol table. And we're going to make that symbol table available as a public property so that it can be used for lookups and also for our unit tests. So um, we'll create a public property for this. And we put that property after the constructor here, and we'll say public. And now this is going to be a dictionary that looks up a string and returns a symbol. And then we create that dictionary in the constructor of the assembler. So now my unit test can collect those labels after the fact. So let's write a unit test for this. We're going to call it, why not call it symbol? So in our assembler, what we're going to do is we're going to run the test, and we'll have multiple instructions in our little program. And so the first instruction is going to be an li. Let's put something into R4, value 9, say. And then we want to create a label at this location, my label. And then we'll create another load immediate instruction that loads something into register 2. The actual values being loaded into the registers here don't matter. What does matter is um, what is the symbol after this? What is the symbol after we've assembled this program? And you'll notice now that the run test method, which was intended for verifying that the bit patterns are still being generated correctly by the assembler, that is no longer appropriate. We now need to create a new method just called assemble that just does the assembly. We don't really want to verify during the assembly. What we want to do is after the assembly verify that our symbol table was correctly uh, or that the my label symbol was correctly installed into the symbols of the assembler. So we'll create a new method very similar to run test, but it doesn't do a verification. So we'll say private void assemble, and we'll just take the assembler client, the program that actually is creating the assembly program. And it will look very similar. In fact, we might as well just steal this here. But then like so. But one thing we will do is we will return the created assembler because we want to start poking at it after the assembly is completed. So we'll return M, which is the assembler. And then in our test, here, what we want to do afterwards is verify that there is actually a label called my label. And also its address should be this location. This first instruction is at address 0, But after assembling that, we will now be at address 4. So we expect my label to have the value 4. So let's verify that. Assert that r equal 4, and then the symbol is in the assembler. I'm going to look up the symbol called myLabel, and that's an unsigned integer. So let's verify that that is. Okay, hold on, I'm fighting against. Okay. Oh, how about that? So we're asserting that the address of the symbol whose name is myLabel is equal to 4. And if there is no symbol, then we will blow up. And so I expect this now to fail. So when we run our tests, that should fail because we haven't actually implemented the logic. So let's run our unit tests, and we should see a failure. There it is. All right, so and the reason is we haven't implemented it. So let's go ahead and implement it. So what does label do? Well, it should check to see if there already is a label called label. If there is, then we have an error because you can't have the same label used twice. So if the label, if the symbols contains the key as label, then we should probably spit out an error someplace. We can put that on the console, I suppose, for now. Console write 9 error. Um, label as label is redefined or was redefined. Hmm. We should probably have a unit test for this. So in order to make this testable, we probably also want to add this to a collection of errors. So we'll say errors.add. Let's just, okay, how about report error? This, and then report error method will add it to a member variable called errors, and also console out write line error message. So now we need to create a place for these errors to live, and they need to be in a list. And then we need to initialize it. Good. Now we go back to our unit tests, and we should create a test that verifies that if we have a duplication, redefinition, then we should complain. So in that case, we assert that asm.errors.count is equal 1. So we should have received an error from that second duplicated label. All right, let's go back now to our assembler and let's actually implement the rest. So here we need to return after we reported the error because there's nothing else we can do. But if there was no symbol, then let's go ahead and add it to our list of symbols. So our dictionary symbols. So we'll say our symbol equals new symbol, and we pass in the name, and then we pass in the program counter, which was called interpreter. Nice. And then we add that to our dictionary. So dictionary is symbols dot add, and then we look it up based on the name, and the symbol is installed. All right. That passed, and then the redefinition also passed. Nice. Let's commit the work that we've done so far. And we'll say added label method to assembler. Nice. So that was one half of the problem. We have now added the capability of uh, putting labels in our program. But the other one is we want to be able to refer to those labels and use them. So what we do then is we want to change the BLT and the jump and link instructions so that instead of having a numerical number that tells the assembler how far backwards or forwards we want to jump, instead what we want to do is make it possible to specify a label instead. So here we go. We'll add a loop head. So that's how jump and link will work. It will take a label, and then uh, that should generate a piece of code that takes us to the BLT instruction. And the BLT instruction similarly wants to have a loop body like this. All right. So now we have to implement this. Now, how would we go about doing this? We take a step back and think about how this would work. Now, um, when we reach the jump and link instruction, the loop head symbol has not yet been seen. It gets defined down here. So at the point where we reach jump and link, we don't know how far ahead loop head is. So what we need to do is remember somewhere that at this position, at this location 8, we wanted to know the address of loop head so that in a later pass, we can then fix up this instruction. Now, this is a very important concept in assembly language programming, and it's called relocation. What we need to do is generate something called a relocation that says later, once the program has been completely uh, parsed or assembled, we then want to go back and fix up all the places where we have all these missing symbols. Each one of those missing or symbol references is called a relocation. So what we need to do is create a relocation for the loop head and create a relocation for the loop body. All right, so what do we do? Well, um, there are a couple of details we have to keep track of. Remember that the jump and link instruction, it assembles into a J-type instruction, but the branch instruction, it assembles back into a B instruction. So we need to be careful about the relocation because the bits that we want to relocate depend on the instruction that is requesting the relocation. So let's go ahead and create a unit test for the BLT instruction first. First of all, let's get rid of these errors. So we'll change this so that this, well, we'll leave this in because we still might want to execute these raw style. But we'll add an overload where we say string target. Now, since we don't know the target yet, we'll just encode a 0 into the instruction that we emit. But what we also want to do is save a relocation. And so we want to do is save the relocation. We want to save the type of the instruction that we're relocating. Basically, what we want to do is save all these three operations or these three operands. So we want to save a relocation. So we'll say emit relocation at the instruction pointer. So in fact, we want to do that before we do the as and b because that will change the instruction pointer. So we want to emit the instruction the relocation. And what we want to do is specify the type of relocation that we want. And this would be a relocation that's appropriate for a B type instruction. And then, well, we also want to specify how to compute the relocation. And so here, we want it to be a relative relocation. So we need to create an enumerate type where we say relocation type, and then we will specify that it's a B, and then it's PC relative. And then we also need to specify the symbol that we want to relocate or refer to. So that is what we need to do. We need to create a method called emit relocation that does all these things. But first, we need to create a relocation class because we don't have that. Oh, no, we need to do the same thing for jump and link, I suppose. Let's go ahead and copy this, find the jump and link, and then make another copy of jump and link that takes a string, which is the target, and then we emit the relocation to the target. Now this is going to be a jump PC relative, and then this is 0 because we don't know yet where that target is located. Good. Now we create the new class called relocation type. Now let's create a new class called relocation. And maybe if we put the right file extension, it would work. Okay, so the namespaces are refun. The class is relocation. And then we also need an enum. Let's make our life easy for ourselves by letting the editor do the work. We're going to create this new method called emit relocation. Let's put that at the end so that it doesn't clutter. Let's put it right next to label, I guess. Here, now this is a private method that takes a instruction pointer. Now, so what we want to do is create a new relocation. I'll pass all those arguments. And then so now we have created a symbol, reference, and the type of patch or update that we wish to do, and then the place at which we want to do that patch. Good. And then we need to add that to a list of relocations that we need to define. And these don't need to be in any particular order. I'll just store them as we see them. And then we need to create a list of those. And then we need to initialize it. Nice. Okay, we have an error here. It doesn't have the type PC relative. Well, let's just generate that. Let's go there. So let's add a dummy 0 value for the enum. Okay, so now we need to collect these relocations, and that's great. We can have a unit test for that, where um, we verify that a relocation gets generated. So in our little test program, we will just create a branch, BLT was it? Uh, we don't really care about these operands, but we do care about the destination, which is going to be my label here again. Why not? And so now what we want to verify is that at the end of this, we will assert that the number of relocations is equal to 1. And also, we will grab that 0th relocation, and this should be count. And then we want to verify that that relocation.name is a symbol name, my label, and that its type is equal to relocation type dot, and this would be a branch PC relative. Okay. All right. So now we need to, well, that's step number one. But the next step is, now that we've generated a list of relocations, at the end of the assembler, once it's run through the whole program, it now needs to position or compute these relocations and patch up the code. So to do that, we need to add a new method to the assembler called relocate. And what we'll do here is we'll actually create a label. This is going to create an infinite loop, but again, we don't care here. This, and let's take the JAL instruction for this purpose, and it does that. Okay. And what we want to assert here is that, well, what we want to do is make sure that the instruction at address 4 is correctly updated. So we will read, in order to do that, we need the memory, I guess. So we'll need to change the setup of this unit test so that we have a memory object that we can always refer to. So let's create a to shut up the C# compiler. We need an array of bytes as well. Okay, so now, right, we want to compare this to what would have been emitted if we had just done a jump and link to -4, because that's exactly what we want. So we'll create another assembler. Let's do that first. Let's collect the instruction that it would have generated if that was working. So we'll say mjump and link to myself. Why don't we add another instruction as well so that it becomes a bit more challenging for the assembler. So we'll say load immediate 4, and we'll do the same up here. But jump and link will, in this case, jump -4. That would take us back to there. So this little piece of code will put in the memory the at address for the instruction that we care about. So the expected instruction is going to be whatever is in memory at address 4. And so what we want to do then is compare. Okay, so now we need to nuke the memory. So we'll say just let's just create a method called given memory. And the given memory will recreate the memory the way we want it to be, and then this becomes a new method. All right. And then we expect this code, after all the relocations are done, we expect those two to be the same. So we need to compare those two. So we are making sure that the actual instruction that our assembler generates is equal to the expected instruction. All right, so if we run our unit test now, it will fail because we haven't implemented it. We haven't implemented relocation yet. So there's our error right there. So this did not happen. So what we need to do now is implement relocations. And so what we'll do is we'll add a new method to the assembler called relocate, which actually performs relocations. All right. So let's go there and relocate our instructions. So what we need to do now is we need to loop through all of our relocations and read the instructions at those addresses and then perform a fix-up or a relocation depending on the type of the relocation. So we'll do this for each of our um, relocation in relocations. Let's create a method called relocate. I'm not sure why the editor is giving me so much trouble. Uh, there we go. And then we create that new method. I'm going to make it private. All right, so what is this supposed to do? Well, first of all, we need to read the word at the given address. So let's, well, before we even do that, let's do some error checking. We have to see if the symbol that we are relocating to even exists. If it doesn't, then we have to give up. So we'll try to retrieve the symbol. Um, so we'll say if symbols try get value relocation dot symbol name out var symbol. If this fails, then we have to report an error. So we'll say something like um, unknown symbol rel dot symbol name. So we'll do that job, and then we return. Otherwise, we have a symbol in our hands. So now what we do is we say, okay, um, uh, depending on the relocation. So let's do a switch on the relocation.rtype, the type of relocation. And if it is a PC relative jump, well, before we even do that, we want to read the bytes of the instruction in memory. And those are going to be in the address that we stored in the relocation. So we'll say memory.read instruction at the address relocation dot. Let's change that to a better name. I'm not liking the changes to the key bindings here. There we go. And why not this? Yeah, I need to customize the key bindings. They've been changed since I just installed a new version of Visual Studio Code, and I am not liking the changes. Okay, so there is the old word, the old instruction, or the existing instruction, I should say. And so we'll say is var uinster is this. So what we want to do now is compute the difference between the current address and the address of the symbol that we obtained, because the symbol has an address, remember? So what we'll do is we'll say um, what is this behavior? I'm going to restart the shell here. All right, here we go. And we lost our work. Wonderful. All right. Well, it looks like I have a few things I need to resolve on my end, so I'm going to stop the session right here. But please do come back and watch me riveted with anticipation as I finish up the relocation work. And that hopefully will be not in the not too distant future. Until then, have a great day.